Good day, class. This is Dr. Ben again, and I want to do one last problem on the topic of the kinematic equations that is in the first third of chapter 4. And so this is a backwards style problem where we're given some equations that describe a physical situation, and we want to interpret those equations and make some kind of conjectures about what might be going on. So we've got this situation where in part A an object is moving along a horizontal surface, and these three kinematic equations are presented to us, and the first thing that we're asked to do is to solve the equations for the unknowns. And so the first equation, we can see that there is an unknown that is listed as T1, and so we need to do a little bit of algebra to solve that equation for T1. So if we leave the units out, we have 9 is equal to 1/2 times 2 times T1 squared. So 9 would equal T1 squared, therefore T1 would equal 3 seconds. That gives us the value of T1. And then the second equation says that the velocity at point 1 equals 2 meters per second multiplied by T1, so that will be equal to 6 then. 2 times 3, and the units for that velocity should be meters per second. And there's one last equation that we can use to solve for the variable T2. So we have 36 meters is equal, minus 9 is equal to V1, which we just found is 6, times T2 minus T1, which is equal to 3. So 36 minus 9 is 27. 27 divided by 6 plus 3 is going to be equal to T2. And so 27 divided by 6 is 4.5. 4.5 plus 3 is 7.5. So T2 is equal to 7.5 seconds. So there we found all three of those quantities. Alright, next part. Draw a motion diagram that is consistent with these kinematic quantities that we have. So the first equation shows us how the position is changing with time, and the acceleration is positive, so that position should be increasing. The second equation shows us how the velocity is changing with time, so the velocity is also increasing with time. And then the third equation helps us to find this value of T2. So basically this object is speeding up, and a motion diagram that is consistent with that should show a train of dots that is getting further apart. And then if I would draw velocity arrows on those dots, those arrows would get longer. And then finally, if I wanted to draw an acceleration, then that acceleration arrow would point to the right. Alright, and so then in the last part of the problem, we're asked to draw a pictorial representation of this. So there's not just one possible scenario we can have, but clearly we have a couple different points of interest. We have this this point 1 and this point number 2. So we're told that the problem involves horizontal motion. So let's draw an x-axis with an origin, and we don't know whether the initial position is at the origin, although actually it looks like we do from the first equation, because the 0 represents the initial position, so we can put a dot at the origin. So that'll be the dot for point 0. And then there'll be another dot to the right for point 1, and then a dot further to the right for point 2. And we have a constant acceleration for the whole problem. So acceleration is going to point to the right. And I think that pretty much finishes that left-hand side. So we decoded these equations to represent an object in accelerated motion traveling to the right, and point 1 was after the start. The object actually started from rest. If we look at the first equation, the first 0 on the right hand side would be in the position of the velocity. Alright, so let's go ahead and look at the second one then. So here it says an object moves on an incline. The application of one of the kinematic equations to that motion is shown below. And so we want to try to figure out some information about this. Alright, and so in this problem, first thing we want to do is solve for the variable that's given, which turns out to be x. So we have 12 squared minus 24 quantity squared is equal to 2 times negative 8, so that's negative 16 multiplied by x. So we'll give this one a try again. So this is part B of the problem that we were working on, where this object is moving on an incline and we're given this kinematic equation of motion. So the first thing that we're asked to do is to solve for the variable, and we can see that in the expression that's given it's the x. So we need to do a little bit of arithmetic and algebra to figure out what this value of x is. So the left hand side is going to be 12 squared minus 24 squared is equal to 2 times negative 8, which is negative 16 multiplied by the value of x. So therefore x is going to be equal to 12 squared, which is 144, minus 24 squared, which is 576, divided by a negative 16. So 576 negative plus 144 equals negative 432, divided by 16 negative equals 27. So the value of x that goes along with this problem is 27 meters. Alright, so we recognize this equation to be the one that is the velocity equation without the time. So it has the form of v final squared equals v original squared plus 2 times acceleration times the change in the position, x final minus x naught. So we can identify some elements here. So we first notice that the final velocity is less than the original velocity in our particular problem, and we see that the acceleration is equal to negative 8 meters per second squared. So that's consistent with the velocity getting smaller, and it looks like the initial position of this object is equal to 0 because of the quantity x minus 0. Alright, so it looks like what we've got here then is an object that is on this ramp and it's slowing down, and so that seems to indicate to me that it's traveling up the ramp because it needs to be slowing down. So if we're going to draw a motion diagram on a ramp, we're going to put a train of dots that gradually gets closer together, and the velocity arrows would be gradually shorter, and the acceleration arrow would point opposite to the direction of motion, which is down the hill. Alright, so now as far as a pictorial representation goes, I believe that we only have 2 points of interest, so we could start our problem at one of these dots, and we could call that the position 0, so it would have an x0, v0, and a t0, and we could end our experiment at any one of these other dots, and we could just call that arbitrarily dot f for final, and it would have a final velocity, a final position, and a final, there we go, time, a final time. And so this object traveling up this ramp is going to slow down as it travels and eventually come to rest and then turn around and come back down again.